Hi guys, and welcome to the last units basically of this class, namely unit 68, 69, 72, then you have 80, 82, and 83. So what are these units talking about? Basically, they're talking, it's a continuation basically of the topic, first of all, on the stars, where they delve a little bit into neutron stars, pulsars specifically, pulsars that is, and then also black holes, okay? So there is a little bit more in-depth analysis of this too, and how basically neutron stars, they produce heavier elements when they actually merge. And also black holes, especially the calculations has to do with the Schwarzschild radius, namely the fact that you equate the this is basically coming from the same idea that we did for the escape velocity from any planet, from any object. So basically equate the kinetic energy with the potential energy. We're using classical mechanics and it works, and here it's going to give us the same answer. The kinetic energy proportional to the speed squared to the velocity squared of the object is 1/2 mass times velocity squared, and the potential energy is inversely proportional to the distance. It's basically g, the gravitational constant, times the mass of the object trying to escape, times the mass of the object that is retaining it from being escaped, divided by the radius. Well, in this case, the mass of the escaping object will cancel from both sides, and then the only thing that you're left with is the radius and the velocity. Now, if I put for the velocity the speed of light, then I will have a condition where the speed of light or light itself is trapped. And that is really what I mean by that. That is the event horizon. So the formula for it gives you basically 2 times g, which is a constant 6.67 times 10 to the negative 11, times the mass of the black hole divided by the speed of light squared. That gives me the radius where light cannot escape if it goes beyond it, okay? Also, some interesting phenomena related to black holes, and to some extent even with the neutron stars, and there is time dilation and also length contractions. There is a phenomenon with the black hole, especially if an object were to go into it, there is a process of spaghettification, basically, where it's going to be stretched in one direction over the others. Then the topics after that, they delve into the Milky Way. Now we're looking at the entire galaxy, about 200 billion stars, okay, including our sun. And when we looked at them, when astronomers looked at them, they classified the stars into basically 2 groups. First of all, you have the stars that are orbiting the galaxy along the arms and also the disk, its plain disk, and those are population 1 stars. And then you have another type of galaxies. Their orbits, first of all, the first ones is population 1, that is more of this circle around the center of the galaxy, and then also they are more toward the basically bluish color. They're of the type O all the way to B. Then you have the reddish stars, which are smaller stars. Those are population 2, and their orbits are, first of all over the place, elliptical orbits, and they exist in the halo of the galaxy, which is the extent where the galaxy, beyond the extent, the visible extent of the galaxy, and also in the bulge, the center of the galaxy. So those are the 2 types of galaxy of the stars in the galaxy. In terms of the formation of the galaxy, our own galaxy, the Milky Way formed about 10 billion years ago when it started to form, and that is probably when type 3 also must have formed. Type 3 or population 3 stars, and those types were the early stars that formed and then one supernova and provided the fuel for the next generation stars. Our own galaxy produces about 10 galaxies a year, about basically produces about 10 stars a year. That's basically about 1 star per month, okay? And it's somewhat an average, basically, a galaxy in terms of star formations. However, this process is going to slow down over time. Yes, when it produces large enough stars, they're going to produce either a planetary nebula or they're going to supernova, and those, they will feed the next generation stars, so the galaxy can still produce more stars. However, the smaller ones, namely the extremely small stars that it forms. Those, they will lock the material in them for a long, long time and basically starve the galaxy from forming further further stars, I'm sorry. So the process, in a sense, is at some point the galaxy will start producing less and less stars down the road. However, there is a process through which basically the galaxy can renew with the star formations, and that is through galactic cannibalism. So what is that? It's basically bigger galaxies taking into them material from smaller galaxies. As a matter of fact, our own galaxy is in the process of taking two galaxies, basically the Magellanic Clouds, which are two satellite galaxies to our own galaxy, the large and the small Magellanic Clouds. And also down the road, there will be a big merger between our own galaxy and the bigger one, which is Andromeda. And as a matter of fact, Triangulum also is another galaxy nearby that is going to be part of the merger. So this process will enhance, if you wish, the process of stellar formations. However, also this galactic cannibalism explains a little bit some of the odd stars and the odd, basically, stellar formations that exist in our own galaxy. So this is in terms of our own galaxy and the evolutions. And we think, of course, whatever is happening in our galaxy is happening, or at least in our local group is happening in other local groups. As a matter of fact, this takes us to the cosmological principle, which basically said that there is no preferred direction. So whatever happens in here must be happening everywhere in the universe. And this is one of the things that Mr. Hubble actually has discovered while looking at the faraway galaxies, that there is a recession. Basically, there is a speed with which all of the galaxies are moving away with us. And there is a law, and that law is known as the Hubble law, which gives us the velocity with which galaxies are receding is directly proportionate to how far they are away from us. And the constant of proportionality happened to be h, which is 2.2 times 10 to the negative 18 seconds, okay? So that is basically something that is due actually to the redshift. And so what is the redshift? Again, if an object is moving away from you, its wavelength shifts toward the red. So you measure how much the shift is, delta lambda, the difference in the wavelength from where it's supposed to be and from where actually it is. And you divide that by the actual value of lambda, and that is what we define in astronomy as the redshift. It turns out this value is critical for our understanding of the evolution of the entire universe, because basically it helps us predict, first of all, how fast the universe is expanding, and it is expanding because this expansion is happening everywhere. Now, and also to see how the universe was before. Now, one critical piece of concept that you really should focus on, it is not that these galaxies are moving away from us. Obviously, if we are on a different galaxy, and by the cosmological principle, if we are on another galaxy, we will see our own galaxy receding away from us with the same law. So this is true for wherever you are in the universe. So what's happening in here, the galaxies are not moving away. What is going on is the space between them is stretching. The fabric of space itself is stretching. As time evolves, space itself is stretching, giving you the illusion that everything is moving away from you. And this is the typical example with a balloon. As you blow it and put dots on it, every dot from every other dot will be moving away from it. Again, if you do the math, you will find that the age of the universe is about 14 billion years, which is just the inverse of the Hubble constant that I described before. It's actually 13.74, but that's basically almost 14 billion years ago. Immediately after the universe formed, about 1 billion years later, our own galaxy started to form. So now the question is, what is the fate of the universe? It depends on a critical value, okay? It depends on the density of the universe. And it depends also on the geometry of space-time. Are we living really in a flat universe? Flat geometry? Or is it a curved geometry? And if it is curved, is it closed or is it open? That's a big question that astronomers are struggling with and astrophysicists are struggling with trying to understand. Obviously, what's the difference between them? In flat geometry, Euclidean geometry, everyday geometry that we deal with, if you draw a triangle and you add the angles inside the triangle, they will all add up to 180 degrees. And this geometry works for us on a very daily basis beautifully. But it's only true on our own scale. But if you go bigger, obviously the Earth is not flat, the Earth is circular, and so the sum of and it's closed, so the sum of the triangle actually are more than 180 degrees. The inside angles of a triangle, they add up to more than 180 degrees. Now, there is another possibility that the universe is open. In a sense, yes, it's curved, but it's open. And if it is open, like a saddleback, basically, of a horse, then in that case, if it's open, then the sum of the internal angles of a triangle will be less than 180 degrees. So this is the difference between them. Okay, how do we know where we are, which universe we are in? Are we in 1, 2, or 3? Well, it depends on, as I said, on the density of the universe, the actual density of the universe. Basically, we measure how much matter is per unit volume in the universe. There is a critical value, again, that is related to the same idea as I mentioned before, namely how the kinetic energies and the potential energy are related. Imagine with me that our own galaxy is contained or is restrained by all of the different matter that is in the universe. So if I take a volume, hypothetical volume of radius r, and see how much that is going to retain our own galaxy, it depends on that density. And if I do the math, and we're using classical mechanics, technically we really should be using relativity, but the answers are very close from each other. Again, the kinetic energy of our own galaxy, which is 1/2 its mass times the velocity squared. And remember, the velocity is related to that Hubble constant times the radius of the same hypothetical volume. So if I square that, and then equate it to the potential energy, which is again G, which is that constant times the mass of our own galaxy, so it's going to cancel from both sides. So it doesn't matter which mass we're going to take, times the critical density, times the volume of the sphere, which is proportional to the cube of that radius, divided by the R, which is the potential energy R. Here is the beauty of this expression. Every R cancels, so it doesn't matter how big the volume you take, small or big. So this is going to give me a value for that critical density. If the density of the universe over the critical density is more than 1, then there is enough matter for the universe to collapse on itself, and we think the universe will be closed. If there is not enough matter in the universe, so either we are at the critical value or bigger, then the universe will expand either critically or more than critically. It turns out that the density of the universe, according to all the best estimates at this point, they're exactly equal to the critical density. Further observation of type 1 supernovae in 1996 proved that the universe is actually expanding at even a higher rate. So there is no question about it that the universe is expanding, okay, even at a higher rate than what we thought initially. The final point of this unit deals with the history of the universe. And there is a standard history of the universe that is really related to how the forces broke up. So you go from 10 to the negative 43 Planck's time. Basically, the unit is also defined in chunks of units of time, so it's not continuous. And before that, we really don't know what happened, but we believe that all the forces were unified. Okay, there is no physics for it to describe us before that moment of 10 to the negative 43 seconds. Then after that, the temperature at that point was 10 to the power 32 Kelvin, a huge temperature. So that is where all the forces were melted into super force. Then after that, gravity broke from the rest of the forces. And at that point, we have the subnuclear matter floating every which way, namely quarks everywhere. This has lasted until the temperature dropped from 10 to the power 32 to 10 to the power 25. And this is a fraction of a second. The universe went through a big expansion at that point because of the fact that those quark starts to form protons, and those protons repel each other, and that probably triggered the inflation stage. We really don't understand also the inflation, but it's necessary to explain what's going on at this point. But this is probably what triggered it. The temperature cooled down with this expansion. As it cooled down, it allowed for more process use. The nucleons started to get closer from each other. As they get closer from each other, the nuclear force actually took over and fused them. And if it fused them, at some point, then the process from radioactivity, another force in nature, switches one of those nucleons, namely the protons, into neutrons, and now you have neutron formations. Then after that, when the temperature cooled, this is we're talking fractions of a fraction of a second. At about 1.5 minutes to about 3 minutes of the age of the universe, the temperature was cool enough that helium started to form, but it's still hot enough. Remember, helium in the stars form around 100 million Kelvin. So this is still super hot still, okay? And that helium started to form, but the temperature continued to drop. So at that point, I'm sorry, I give you, it's about 5 million when helium starts to form. So a few million kelvins at that time, it's still super hot. Anyway, the point being in here is that the helium formed, it formed in about 24% from the original protons that we had in the universe, plus the amount of helium that formed, and then at that point, matter started to form. There are probably traces of lithium and beryllium, but that's about it. We have 24% of helium. This process explains beautifully. The universe remained super hot still, to a point where all the radiation, namely light, namely photons, did not escape from it, because at that point the universe was still too hot. Any photon trying to escape will collide with the next atom. And actually the photons themselves had a tremendous amount of energy, that they were forming pairs of electrons and anti-electrons, namely positrons, and those pairs also were getting destroyed in the process after they form, until at some point we have the matter that we know it. There was an imbalance actually of the matter over antimatter, but that's something that we don't understand, how come that symmetry was broken early on in the universe. Now, the point being in here, the universe cooled down around 380,000 years after that. It cooled down to about 3,000 Kelvin, where light started to escape. This is where we got the CMB, the cosmic microwave background radiation that we discovered in the 50s, and that proves how the process went. From that point on, the universe became visible, transparent, okay? And like before, which was opaque. As I was saying, immediately matter starts to coalesce. Probably dark matter played a major role in bringing matter together, and that formed stars, and those early stars started to explode, and then the galaxies started to form about 1 billion years later. Our own sun actually formed about 8.8 billion later, and from that point on, our galaxy, our star, formed, and now it's about 4.5 billion, and its age, we are at 13.74 from when the universe started forming. So this is basically, in a nutshell, the standard history of the universe, and these are all of your units. If you guys have any questions, please let me know. We have a review that is coming. You watch for the announcements, and we have our final, which is going to be on June 1st. Thank you.